Hi everyone, Mr. Fong from TSA, the Science Academy here. I believe all of you are very familiar with this scene. Clearly I wasn't trained in this, but it is indeed true that sound can actually cause glass to shatter. Now, how do we do this and why does it happen? Any physical object has a frequency at which they naturally vibrate. When you flick the glass, these waves sense impact throughout the glass, interacting with one another. These interacting waves will amplify at some parts and cancel out at some other parts, which results the glass to vibrate at its natural frequencies. The vibrating glass then pushes and pulls the surrounding air, which sends a sound wave that reaches your ears. Now, when a sound of the same frequency is directed at the glass, the incident sound will act as a driving force, and because of the energy transfer that is in sync with the vibrating glass, this causes the vibrations to amplify, and eventually it will cause the structural integrity of the glass to break and shatter. The phenomenon is known as resonance, and that's why the natural frequencies of an object is known as resonant frequency. Resonant frequency is important when it comes to building a structure. It helps engineers ensure that the structure can withstand dynamic loads such as wind, earthquake, and even vibrations of heavy machineries. If the external driving frequency matches with the structure's natural frequency, resonance can occur, and this may compromise the structural integrity. Take Tacoma Narrows Bridge for instance. There are several factors contributing to the collapse of the bridge. Wind is one of them. Wind that was hitting the bridge splits up and periodically shakes off bunches of air above and below it in an effect called vortex shelling. This acts as a driving force, setting the bridge to oscillate initially. This vortex shelling effect resulted in resonance occurring, creating large vertical undulations in the bridge's motion. However, small twists in the bridge's motion allowed more surface to come into direct contact with the oncoming wind, increasing the incident force and amplifying this torsional oscillation. With the wind striking the bridge periodically, a feedback loop was formed, warping and twisting even more. The bridge, essentially fluttering in the wind, eventually collapsed due to the large enormous strain on the structure. I suppose one can say that the Tacoma Narrows Bridge has crossed over to the other side. This failure has led engineers to incorporate aerodynamics into their future designs to prevent such disastrous things from happening again. Or, just to be safe, perhaps not cross a bridge on a windy day. Curious minds, everyday discoveries.